Alrighty, thank you very much everyone for coming. I'm excited to tell you about tribocharging this morning. Let me just make sure I have the right direction. There we go. Okay. Tribocharging is a process where materials come into contact with each other and then transfer charge when they contact. This effect is more pronounced in the permanently shadowed regions, polar craters, and the night side of the moon. Charged dust can stick to spacesuits and surface assets and cause degradation and damage to equipment. The charge can also be harmful to sensitive electronics, and accumulated charge poses an electrostatic discharge risk to astronauts. This effect has been studied and modeled using work function models, and what I'm going to be talking about today is a different approach using a different model. So what we use, we call a patched surface tribocharging model. And for this model, we create a synthetic surface using a stochastic algorithm. So the picture on the bottom right there kind of shows you what the surface looks like, where the pink areas would be charge donors and the blue areas would be charge acceptors. And so we have control over things like the surface size, the patch size, and the donor probability of our surface. So we can adjust it to give us the charge. So we can adjust what the surface looks like so that it exhibits the charge parameters that we want to investigate. This model has been implemented in LIGHTS. LIGHTS is the open source discrete element modeling software that we use in our lab to model interactions between hundreds of thousands of grains that in this case would represent regolith particles. So on the bottom left, you can see a description of what two particles would look like with these charge patches. So a postdoc in our lab implemented this model for charge exchange between these DEM particles. And so we have validated the patch model for interactions between DEM grains. That's wonderful, and it's a great first step to what I'm trying to do. Ultimately, what I want to model the charge exchange between a rover wheel and grains in a dust bed. So if you think about the picture there on the left, you have the wheel spinning and it's stationary and it's kicking up a bunch of charged grains. So I want to be able to pick out a single grain and look at what is the charge in this grain and also what is the overall accumulated charge on the wheel. So to be able to do this, first, we need to implement and validate dynamic interactions between mesh objects and DEM particles in our simulations. So for our real implementation, we want to be able to use a mesh object instead of having to construct it out of a bunch of DEM particles stuck together. And then after looking at the dynamic interactions, we want to expand our current tribocharging model to include DEM particle mesh object exchange interactions. So to validate grain mesh interactions, I did a bunch of physical tests that I'm not going to tell you all about. I'll just focus on 3 highlights. So I'll tell you about normal force, normal impact, and cohesive force tests that I did. So for our cohesive force test, we had a stationary mesh plate and then a DEM particle. So we start the simulation off with no gravity, and the DEM particle is stuck to the plate with some given cohesive force. Then we switch on gravity in our simulation, and we know that our test is a success when the particle detaches from the plate if the cohesive force is less than gravity, and the particle remains attached to the plate when the cohesive force is greater than gravity. Next, for our normal impact test, we have a DEM particle, and here it's a mesh cube. And these are provided with equal and opposite velocities so that they collide head-on. And we repeat this test with a range of coefficient of restitution values, and our test is successful if the post-collision coefficient of restitution is equal to the input coefficient of restitution. And something interesting to note in the graph on the bottom right is you see there's a subtle difference between the pink line, which is our DEM particle only simulation, and the blue line, which is our DEM particle mesh cube simulation. And this is a very, it's not a significant difference. It's on the order of 1 to the -5, but it's notable, and I will tell you about that later. And then finally, in our normal force simulation, we have a bunch of particles stacked on top of each other, and we let them fall under gravity, and they should not move or rotate laterally when they collide. And again, here, note the small difference between the final positions so the pink grain there, it was either a STL particle or, a DEM grain. And so the final difference between the position of that grain is on a millimeter scale, and the particles here were like meter-sized particles. So it's a very small difference. So moving on from the dynamic interactions, now we want to look at charge exchange between these particles. So the video here shows, I just repeated the normal force simulation, and it shows particles that are stacking on top of each other. All of these are DEM particles, and you can see that they have exchanged charge. So the middle particle has lost some charge, and the other two particles have gained some charge. So ideally, what I want to do is I want to take that current blue particle, replace it with a mesh file, and see the same behavior. Shockingly, we are still working on that. So here, you can see a similar video, and that just kind of like shows you the motion. So the gray here is a mesh file. And the reason why we're having some trouble applying our charge to these simulations, like I mentioned before, when you saw the slight difference in our coefficient of restitution simulations, handling facet-based mesh contacts is not the same as looking at smooth surface contacts. And so what is happening is it's very hard to figure out what is the exact contact area between our mesh surface and our smooth DEM particle. And since the contact area is very important for calculating the charge exchange, we're having like a little trouble there, but we will figure it out. So again, we're trying to move towards a rover in a grain bed simulation. The picture is kind of like the ideal world. We have implemented and validated a 6 degree of freedom integration model in LIGHTS that allows us to have physical interactions between our mesh files and our DEM particles. And we are now working on, like I mentioned, developing the contact charge exchange between mesh files and DEM grains. And then after we have done that, we will add in electric field contributions to our simulations as well. Alrighty, thank you very much. I'm happy to answer questions later.